Hello statistics students, this is Emigh, and this video is our discussion on section 8.1, Basics of Hypothesis Testing. I like to teach hypothesis testing through an example first. So we have this example here. Results from the XSORT method of gender selection involved 100 couples who gave birth to 58 girls and 42 boys. The Genetics IVF Institute claims that its XSORT method allows couples to increase the probability of having a baby girl. Use the alpha equals 0.05 level of significance to test the claim. Use the critical value method and then the p-value method. Okay, so I'm going to do these two methods side by side. This first one here is the critical value method, and this one here will be the p-value method. Seeing them side by side will help you see their similarities as well as their differences. Okay, they both start out the same, these two capital H's. Top one gets a sub 0 because it is the null hypothesis. Bottom one gets a sub 1 because it is the alternative hypothesis. This claim is about proportions, so we use lowercase p. Null hypothesis always gets an equal sign, and the current proportion would be 0.5. Think of it as 50-50 for having a boy or a girl. But this claim says that they can increase the probability of having a baby girl. So we put the greater than 0.5. So they're saying they can make it greater than the current 0.5. Okay, with the critical value method, I would then draw a graph. Don't be afraid to sketch these. They do not have to be perfect. Put your Z at the end. 0 in the middle. Now, because it said it could increase the probability, we're going to cut off the tail up here. And that represents the rejection region. So that is where our alpha of 0.05 is the area of that red shaded region. This z-score right here, we call the critical value, hence the critical value method. And you guys know how to find the critical value. You run inverse norm. Inverse norm requires the area to the left of the critical value you're interested in. Well, the area to the left would actually be 0.95. So do this with me. Pick up your calculator, hit second, distributions, scroll down to inverse norm, open that up, area to the left is 0.95, mu is 0, sigma is 1, run that program, and it will give you your critical value. Turns out that our critical value is approximately 1.645. Okay, now what we're going to do is look at their data and see if their test statistic falls in that red rejection region or not. Okay, the way we find the test statistic is by running this test called one prop z-test. Okay, so do this with me. Pick up your calculator, hit stat, arrow over to tests, and scroll down to this conveniently named program, one prop z-test. 1 stands for one population. Prop is because the claim is about proportions. Z for standard normal distribution, and test because this program performs hypothesis tests for us. First thing that the first input that the program wants is p sub naught, which you did in the steps with the capital H's. It's 0.5. Next thing it wants is our number of successes. Success in this problem is considered having a baby girl, so there were 58 of them. Next thing it wants is n, which is our sample size of 100. And the last input it wants is the inequality that we decided to use in the alternative hypothesis, which looks like that on your screen. So make sure that one's highlighted. and then run that program. The very first thing it outputs says z equals 1.6. That is our test statistic. I just write TS for test statistic, and it looks like we got z equals 1.6. Now what we do is graph the 1.6 on the horizontal axis. Well, 1.6 is closer to 0 than 1.645, so our test statistic of 1.6 did not make it in that red shaded region, the one we call the rejection region. So we are not going to reject it. Had it fallen in that shaded region, we would have said, okay, reject, but it didn't. So we say fail to reject. The null hypothesis. Okay, after we make our decision, either to fail to reject or reject the null hypothesis, then we state our conclusion. We start with the word there. Since it's fail to reject, we would say is not. And in a few slides, I've got this all broken down for you. There is not evidence to, now we have to decide on the word reject or support. Has nothing to do with our decision of failing to reject. It's that the alternative hypothesis did not contain equality, so we use the word support. So there is not evidence to support the claim that and then you just restate the claim. The claim that the XSORT method increases the probability of having a baby girl. Okay, so I'm going to show you the p-value method now. Like I said, they both start out the same, so we're going to do those capital H's again. Lowercase p, because the claim is about proportions. Always an equal sign. Increase came from the wording of the claim, and the current proportion goes next, 0.5. Okay, now instead of drawing the graph, we run that one prop z-test. And so let's do that again together. You hit stat. Well, if you turn on your calculator screen, it's probably still there, but in case you cleared your screen, you hit stat, arrow over to test, scroll down to one prop z-test. All those same inputs as before. Your p sub naught is the current probability, which is 0.5. Your number of successes, or there, was 58. Lowercase n is the sample size of 100. And then the alternative hypothesis based on the claim was the greater than inequality. Okay, but this time we're not looking for that first output. Let me run mine real quick. Okay, we're not looking for that first output, that z equals 1.6. That was the test statistic. What we're looking for this time is the p equals. So on our output we get this p-value of 0.54, we'll go with 8. So our p-value, or the probability of making a type 1 error, is 0.548. That's pretty high probability of making an error. So what we do, oh gosh, I have a typo there. It's 0.0548. Okay. All right, so what we're going to do now is compare our p-value to our significance level. That was this one, if you recall. And that would be let's see how to best write this. Let's write it like this. P-value compared to our significance level alpha. Okay, so our p-value is 0.0548, and our significance level is alpha equals 0.05. Comparing these two values, our p-value is greater than our significance level. And so we have this little rhyme that we say, if p is high, the null will fly. Okay, then we would switch to our blue and we would write exactly the same thing that we have over here. If the null will fly, that means it's good. We're not going to reject it. We're going to fail to reject it. And that would lead us to the same conclusion of there is not evidence to support the claim that the XSORT method increases the probability of having a baby girl. Okay, so those are the two methods side by side, critical value method and the p-value method. And what the next handful of slides is going to do for us is really break down the general form and all the thought processes in between the stuff you saw me write down here. It's going to fill in all those blanks for us. Okay. Critical value method compares the critical value and the test statistic on the horizontal axis. That's why we graphed that one. Contrary to the p-value method, that compares the area, called the p-value, the probability value, to the area alpha, called the significance level. We have multiple tests we can run, or programs we can run for hypothesis testing. We went with one prop z test because our question was about proportions. But if your question is about means, you may need to run the t-test, or you may need to run the z-test. So these two are only for problems about means. This one is for problems about proportions. Okay. How to write the null and alternative hypothesis. You always do the capital H sub 0 for the null hypothesis, and you always use an equal sign for that one. For the alternative hypothesis, it's always H sub 1, and you have three options for your alternative hypothesis: less than, greater than, or does not equal. Now, there is a case, or there will be cases, where your claim contains equality. What I mean by that is they claim to equal something, they claim to make it less than or equal to, or greater than or equal to. So if their claim contains one of these three symbols, well, we have a problem because you're not allowed to use those three symbols in the alternative hypothesis. We're only allowed to use these three. So what you do is you use the complement. Let me erase all this stuff. So if your claim is an equal sign, you use the complement, which is does not equals. If your claim is less than or equal to something, you use the complement, which is the greater than sign. And the last case would be if the claim is about greater than or equal to, you would use the complement, which is the less than sign. Okay, whatever sign you use determines which graph you draw. For example, if the sign you used was the less than sign, then you draw a left-tailed graph. If the sign you went with in your alternative hypothesis was a does not equal sign, then you cut off both tails. And finally, if the sign you went with was the greater than sign, then you cut off the right tail. Okay, if you recall, the next thing we did was find that critical value. We did that by running inverse norm. So same thing here. If your question is about proportions, you're going to run inverse norm to find the critical value. If your question is about means, you're going to run inverse t. And again, if your question is about means, but you know what sigma is, then you run inverse norm. It's all the same strategy as confidence intervals. Whereas what I mean by that is if the question is about means, you're going to have to decide between z and t. So you can always go back to that flowchart from chapter 7. At the very top, it's a huge title that says how to decide between z and t. This is z. Anytime it says inverse norm, that's the z I'm speaking of. And if your claim is about standard deviations or variances, that's chi-square distribution, we would use the program called Math 200B. Okay, if you recall, the next thing I did was find the test statistic. And these are the formulas if you want to find the test stat by hand, but we didn't do that. We ran one prop z test. You may find yourself having to run the t-test. That would be if your question is about means. You may find yourself having to run the z-test. Again, that's if your question is about means. How do you differentiate between z and t-test and z-test? It's always about sigma. It's always about sigma, sigma, sigma. Okay, and if the problem is about standard deviations or variances, then there isn't a program for that one, so we would use this formula to find the test statistic. All right, what we did next was we put that test statistic on the graph. If that test statistic is in one of the red tails, that makes our decision for us. We reject the null hypothesis. But our example was different. If ours is aligned with this here. If it is not in one of the red tails, then we will fail to reject the null hypothesis. Okay, for the p-value method, at that point we found the p-value, and we did so by running one prop z test. So I think we have a little typo here. Let me get these up and fix this. I see a problem. For problems about proportions, you will want to use, that's wrong, just like we did, one prop z test. Problems about proportions, one prop z test. Or if you don't have everything you need to run the full one prop z test, you guys can run the program you know called normal CDF. Now, next one, if your problem's about means, then that's where the typo went in place. Those two got swapped. And you know what the population standard deviation sigma is? That's when you'll run the z-test. For problems about means, population standard deviation unknown, you'll run the t-test. And finally, for claims about standard deviations or variances, you can run chi-squared CDF, which will request the lower, the upper, and the degrees of freedom. Okay, to compare the p level to the significance level, there's like that little rhyme that I said we use, and so here it is written down for you. If p is low, the null must go, and that would mean reject the null hypothesis. If p is high, the null will fly, and we will fail to reject the null hypothesis. So the example we did, p was a little higher than alpha, so that's why we failed to reject the null hypothesis. Okay, when you guys are running these programs, one prop z-test, z-test, t-test, you may find an output that looks something like this. P equals 2.5 capital E minus 7. So when you first learned scientific notation, well, most of us, it looked more like this here. Hopefully that looks familiar to you. That represents a very, very small number. You'd have to move the decimal place 7 times in the direction that would make that number small. That's because of the minus sign before the 7. But on your calculator, it's going to output like this with the capital E. So when you're running a hypothesis test, you'll often find scientific notation for your output, and then when you move the decimal place, you get a value something like this here. And if you're asked to round to 3 decimal places, you'll end up putting 0.000, and that's okay. Don't let that make you think you did something wrong. To have a p-value approximated at 3 decimal places as 0 is just fine. It's within the allotted range. And the next example here has a positive 13 after the E. So you would move that decimal in the direction to make that number very large. And here you can see it is in standard form, 25,649,300,000,000. Okay, after you have made your decision to reject the null hypothesis or fail to reject the null hypothesis, then you can write your conclusion. And don't try to get to your conclusion before you've definitely decided on your decision, because the wording of the conclusion is completely based on that decision. For example, you have 3 blanks to fill in. You start with the word there, and the first blank is going to be is or is not. The second blank is going to be support or reject. And the third blank, you just restate the claim that you were testing. Okay, so how do you decide between is or is not? Blank number 1. If your decision was to reject the null hypothesis, then you would say there is sufficient evidence. Only other case would be your decision was to fail to reject the null hypothesis, and then you would say there is not sufficient evidence. The second blank, support or reject. How do you decide between the two? And this decision goes way back to the original claim. If the claim did not contain equality, that would be a claim that was strictly less than, strictly greater than, or strictly does not equals. If the claim was one of these inequalities here, then you would use the word support in that blank. And the only other case is if the claim did contain equality. So that would be a claim that would be contain less than or equal to, greater than or equal to, or an equal to sign. And if that is the case of the original claim, then you would put the word reject in that second blank. One way to help you remember is support and reject. Those are complements of each other. And just like if the claim contained equality with one of these, we had to use the complement, which was one of these here. So, third blank, you just restate the claim. Okay, type 1 versus type 2 errors. I think of it as a false positive and a false negative. Now this only comes into play if you made a mistake, of course. So let's look at our table here, which outlines the 4 possible outcomes. Okay, so let's say that the null hypothesis is true. So I'm looking at this column, and you decided to fail to reject the null hypothesis. So you made the correct decision, okay? Makes sense? Let me erase that now. Second case, in no particular order. The null hypothesis is true, and you decided to reject the null hypothesis. You have made what is called a type 1 error, and alpha is the Greek letter, lowercase alpha, that we use to represent the type 1 error. That happens when you rejected a true null hypothesis. Erase that. Next case, the null hypothesis is false, and you decided to reject the null hypothesis. You made the correct decision. And last of the 4 cases, again in no particular order, the null hypothesis is false, and we failed to reject it. Here we have made what is called a type 2 error, That is failing to reject a false null hypothesis. Probability of a type 2 error is equivalent to the Greek letter beta, and that's a capital beta. So I'm going to erase all of that, and just want to highlight right here the probability of a type 1 error is alpha, and the probability of a type 2 error is beta. Now you've seen alpha before. That right there is called our significance level. Every problem should tell you what significance level they want you to use. If for some reason they don't, you can use the default, which would be 0.05 for alpha. Alright, so here's an example. A type 1 error is the mistake of rejecting a true null hypothesis. So if we conclude that the probability of having a baby girl is greater than 50%, when in reality it was not, that means our data misled us and we made a type 1 error. So I'm using the XSORT method results for this example. A type 2 error is the mistake of failing to reject a false null hypothesis. So according to that example, that would have been there's no evidence to conclude the probability of having a girl is greater than 50%. And again, it's our data that misleads us. Don't accidentally think that these errors are because you made a computational mistake. These errors are due to the data misleading you. You don't have enough of it, it wasn't gathered correctly, you have a biased source. And sorry, to finish that example, I went off on a tangent, but in reality the probability is greater than 50%. And that is our discussion on section 8.1. Thanks for joining me, and I will talk to you soon.